Lisa Randall from Harvard, and her title is Black Holes and Quantum Gravity at the LHC.
Hello. I also want to say it's really been a pleasure to be here for the time I've been here, and thank you for inviting me. Just to have some generalities, since this talk is a little different than what we've heard so far. Of course, the LHC is rapidly approaching, and so the question is, what should we be doing at this point? And I think I'm going to stand on this side so I can actually look at you. So the question is what we should be doing at this point. And there are many challenges, and a lot of work is being done to try to optimize the types of experiments people have already thought about. There's a lot of work going into finding precise measures for low energy supersymmetry, for example. But the question that I've had is sort of, are we doing not just the best searches that we can, given what we know, but also are we doing all the searches that we can? And in particular, there's a lot of evidence these days that point to physics appearing at higher energies. And by higher, I don't mean necessarily extraordinarily high, but once you start getting into the TeV range, experiments at the LHC get really tough. And so how do we go about asking that question for what things we should be looking for? Well, we can do first principles calculations, try to come up with, or we could just do models. And we can just ask what we think there might be. What are the generic types of things? And I think Natty gave some sort of estimate for low energy supersymmetry of being something like a non-zero probability. And I think we could probably say that for several different models. And it's not that we necessarily think any one of them is going to turn out to be right in the end, but I think we should be thinking broadly about what are the possibilities for what can happen. In particular, there could be low energy things that we're thinking about, and I think there the question is, there the hope is that you have so much stuff that you have trouble telling it all apart. But it could be that you're sort of in the TeV range, and then your question becomes, what is it that you can actually look for? And so I think thinking about extra dimensions is one way of thinking about that question, because a lot of the interesting physics might not show up until you get to sort of the TeV scale or even higher. So it's also a way of sort of broadly thinking about what strongly interacting physics can be. So I think it's very worthwhile to do that. What I'm going to try to tell you today is that in the context of thinking about it as a strongly interacting theory, there's even some hope that if we really have higher dimensional solutions to the hierarchy problem, that we'll have low scale of gravity, and perhaps we can actually distinguish among different models of quantum gravity. And just to be very clear, it's going to be a very phenomenological approach, but it's going to sort of point to some interesting questions to be asking. I should say this is all work that I've done in collaboration with Patrick Mead. So the first question is why people, so as I said, the title of the talk is Black Holes and Quantum Gravity at the LHC. And certainly one of the things that a lot of people, certainly those people who aren't actually doing physics, get excited about is the idea that there might be higher dimensional black holes produced at the LHC. In fact, many people are worried about it. But in fact, it does seem like an extremely exciting signature. Why is that? Well, you could just do a simple dimensional analysis estimate. You just say the cross-section is pi r squared, and you just replace r by 1 over m, where m is your quantum gravity scale. If you're dealing with a scale about a TeV, that means that even at threshold, you're talking about 100 picobarn cross-section. If the LHC gets tens or hundreds of inverse picobarns, then you're talking about large, femtobarns rather, you're talking about large numbers of events, 10 million events perhaps. So it sounds great. It sounds very like there should be tons of events, and there's lots of interesting things to look for. And why is it so big? Well, it's not suppressed by gauge couplings or phase space factors. So people talk very optimistically about prolific production, spectacular fireball signatures, etc. In this talk, I want to really think about this a little bit more clearly and really look hard at the number, look a little harder at the numbers, and ask, do we really even produce them? And the basic problem is that the part-time distribution functions fall rapidly. So if you go a little bit above a TeV, you start seeing less and less events, and you start seeing that really rapidly. And I'll try to show you some of the numbers to show you why we really have to be worried when we're really dealing with TeV scales. And I'm going to argue that the LHC is actually quite unlikely to really make, certainly unlikely to make black holes that are really in the classical thermal regime that decay with high multiplicity via Hawking radiation. However, I don't think that means that we will necessarily see nothing. We might actually see signs of strongly interacting physics. And in particular, I'm going to focus on prolifically produced two-body final states. Now, we're going to be in a regime where we're not going to trust classical calculation for black holes, for example. But I'm going to look at different models and show you how, by looking at these two-body final states, we might actually be able to distinguish among different models of quantum gravity. So the first question is, why is this change in expectations? Over a period of 5 or 10 years, whatever, we've gone from thinking that we're going to have this enormous number of events, and now it looks like it just doesn't look as good, and I'll tell you the detailed reasons why. But just to give you some overview, I think, first of all, the estimate was always a bit optimistic. And so basically, if you're going to make claims like that, you really want to just go back and make sure you understand all the uncertainties in the predictions and the refinements. And the real thing is just that, as I said, the distribution functions drop really rapidly. And the point is, we're always going to be near the threshold. There was the factor of m black hole over m. And it's not really right at m that you're going to trust that you're producing classical black holes. And so the question is going to be how high above m you have to go, and how high in energy you really need to get to make these things. So in particular, there's really only two terms in that estimate. There's m and m black holes. So I just want to first, before telling you what I think we can do, I want to first think a little bit about what those black hole predictions were and why you might want to be a bit wary. Okay, so just to set the stage, we're going to be considering both large extra dimension black holes, which is what most of the literature has focused on that's discussed black holes. Those are the models that just have a low scale of higher dimensional scale of quantum gravity, which is low. We're going to concentrate in the numbers I present on the case n equals 6, that's to say n 6 equals 6 extra dimensions. The reason for that is that's just the least experimentally constrained, and the bound there is about, the gravity scale there is greater than about 900 GeV. The other thing I'm going to consider are RS warped extra dimensional models. They're often not considered when people think about these classical black holes. That's because it's a warp theory, so it's anti-de Sitter space, it's not flat space. But what's often neglected is the fact that there is this regime between the anti-de Sitter scale and the quantum gravity scale, where you would expect black holes that are basically approximately flat. So to the extent that there's a ratio of m over what I call k, which sets the ADS scale, you should be able to make things that are like flat 5-dimensional black holes. The ones that are at higher energies just look like strong bound states. People also sometimes confuse in the literature with these pancake-like black holes on the UV brain. But on the IR brain, you have a chance of making things that look like 5-dimensional flat black holes. And the bound there on m is about 500 GeV. So I first want to consider what was that m that was in that estimate. Remember, we had something like 1 over m squared. Well, the first point is a kind of obvious point that m is convention dependent. You have the normalization for your gravitational action. I give the Myers-Perry convention. And it's just, when we first started looking at it, it's worth noting that there are 3 different conventions in the literature. The higher dimensional case, the large extra dimension case has two different conventions, which particle data group uses the one that's labeled Feng there. There's another one that was used by the original Dimopoulos-Landsberg paper, and we used a different one for the warp scenario. And although, you know, you might say, who cares? Well, if you asked what that threshold scale was, it's m or 1.6, it's m Planck or 1.6 MD or 2.9 m. And these might sound like small numbers, but what's going to keep happening is these small numbers actually make a big difference, because the difference between producing something that's 3 TeV and 1 TeV in the LHC is enormous. So it sounds like a small number, but actually in terms of the actual rates you get, it could make a huge effect. The other question, of course, is what is m black hole? And one question you might ask is, when do you really start making black holes? And that's the real question. I mean, clearly we want energies greater than m, but as we just said, m is convention dependent. So what do we really mean? Well, there's a number of ways you can ask the question. So it's really a mushy question. There's not a very precise answer to this question. But I'm just going to consider things that you might consider at least the minimum criteria you would want to have if you're going to be talking about something that you consider some classical black hole. So one might be that you want the Compton radius to lie within the Schwarzschild radius. And so you just put in a factor of 2 pi and m over 2, which is the energy of each of the colliding particles. And you get a more stringent version of the above, which was just m black holes greater than m. And in fact, you find for the n equals 6 large dimension scenario, you're already up to 4m. And remember, m was already bounded at 900 GeV. So that would already put you at 3.5 or 4 TeV. And in the case of RS, you're in even worse shape, because you put that in, you get 16m. So that's not looking that's not looking great, because you're already saying, if you really trust that criterion, you're already at the regime that you really don't think you're going to be producing an enormous number of true black holes, just from that simple criterion. That's not actually all the criteria you might want. You might want to put in a few extra criterion if you really want things to be thermal. After all, we have this finite mass object, and we want to ask that it's thermal. So in the literature, you sometimes see a criterion of a parameter called x min, which is basically defined with respect to the admittedly convention of n_m, but it just asks when do you really trust that you're producing black holes. So that we're going to use this parameter x min. And just some useful formula to keep in mind when we're talking about n extra dimensions. You can relate the Hawking temperature to m and md, or whatever you want to call your quantum gravity scale, through this factor k of n. That k of n ranges from about 1/2 for the RS case to about 2 for the 6 extra dimensional case. And there's a formula for the entropy in terms of m over t. And so clearly what you're looking for are bigger entropies, and the question is, how big do you really need your entropy to be to trust that you're doing anything that makes sense? So just a few more formulas, and this is going to be important when I give the criterion in a minute. We also used formulas for how many particles you produce when you have decaying black holes, because that's going to be relevant, how many degrees of freedom you really have in your black hole. And so, so one thing to keep in mind, which is kind of often, so you can solve for the number of particles just by assuming Hawking radiation. So you can assume Hawking radiation, solve for your number of particles. And you find some formula that has some sort of order 1 number times m black hole over m to some power, which is greater than 1. And you see that if you're at threshold, the number of particles you produce would be not even bigger than 2. So you certainly don't trust that you're really making thermal black holes at that point. So you clearly have to get a little bit higher. One thing I want you to note, though, also is that these formulas assume that you're decaying on the brane. This sounds like a small point. So the point is that you have these black holes. They're really bulk black holes, but it was shown that actually a significant, just because of the large number of degrees of freedom in the Standard Model, a big fraction of the decays will occur on the brane. Horowitz and Meyer wrote that up. I think Lenny also had talked about that. So basically, the thing is, though, that if you have particles on the brane, at a given temperature, they actually have less energy than particles that would be in the bulk at that same temperature, just because they can oscillate in fewer directions. So if you were to actually calculate this, assuming you really had decays in the bulk, which is one way of estimating your true entropy for your black hole, because after all, it really is in some sense a higher dimensional black hole with higher dimensional degrees of freedom, where you have gamma 4 and gamma 3, you'd actually have gamma 3 plus n and gamma 4 plus n if there are n extra dimensions. And that's important because if you have if you calculate a certain number of particles, but you're actually asking about the entropy so that you trust that it's a thermal state, you should be multiplying by some factor to correct for that. Okay, so that'll become clearer now. Okay, so what are the constraints you'd want to put on x min to say that you really have something that's thermal? I mean, the point is just, we know x min better be bigger than 1, and we just want to figure out, does it have to be 3, 10, whatever. I mean, if you just believe that Compton radius, smaller Schwarzschild radius, you're already at pretty high values. But I mean, one condition you want is that when you're decaying, you have a small back reaction on the temperature. That actually turns out to be not just a strong constraint in this case. But an important one is that you don't want an individual degree of freedom to carry some finite fraction of the mass of the black hole. I mean, it's hard to believe you would have a thermal object if both of them carry m over 2, for example, if you have 2 degrees of freedom carrying m over 2. So if you just ask that, and again, this is where this factor of 3 versus n plus 3, these gamma factors are relevant. So if you want to have bulk particles and require that their energy is much less than the black hole mass, even if you have a single particle, you're already up to x min about 3 for RS and x min for 2 for ADD, and that's only for a single particle. So you can see that you really you really need x min to be fairly high, and I'll show you a plot of that in a second. Another criterion is that you'd want the black hole lifetime to be bigger than 1 over m, so that you have anything that looks somewhat resonance-like. And really, an even stronger criterion in some cases is that you want it to be bigger than the Schwarzschild radius, so that you have enough time for the black hole to equilibrate as it decays, re-equilibrate as it decays. So I just plotted these various constraints here. This one and this one are for lifetime, and this one is just about the individual degree of freedom. So this was a single degree of freedom carrying the black hole mass. So you see, this is for ADD and this is for RS. And you see, even that criterion is already putting you up at x to 3 or 4. And if you want it to carry half the energy, you're just getting up to high x's. So the point is that you have to be well above the threshold before you really can believe that you actually have something that's truly a thermal state. And the same thing applies in RS. Very conservatively, you might say very optimistically, you might say x min is about 4 or 5, but that would be ridiculous. No one would really believe that's a thermal state. Okay, so what do we conclude from this? Well, obviously x min, the threshold energy, cannot be m, which is sort of what was assumed in that original estimate. I mean, don't get confused. Black hole cross-sections look like they're growing with energy, because you have that factor of m black hole over m to some positive power, but the parton distribution functions are falling really rapidly. So as you ask to produce heavier black holes, that is to say you go to x min bigger than 1, your actual production rate is falling very rapidly. So, and just as an aside, not knowing what x min is actually makes it difficult to bound or extract m, even if you did these experiments. And that's just an aside that I can come back to if people are interested. Okay, so far we've said x min, it has to be somewhat bigger than 4 or 5 at least. But what about the real threshold energy? Well, it's even worse than what I've just said, because actually only a fraction of the energy would be, if it was a black hole, only a fraction of energy would really get trapped behind the horizon. So it's conventional to define an inelasticity parameter, the black hole mass divided by the square root of S. And again, this is important because your PDFs are falling so rapidly. So based on the work of Penrose and the wonderfully named Death and Pain, Irving and Giddings did some work where they collided together two shock waves and asked what fraction of the energy gets trapped behind the horizon at zero impact parameter. The original guys did for zero impact parameter. They extended non-zero impact parameter, and Yoshino and Richkoff refined that calculation. And it turns out this inelasticity is an enormous effect, because if you look at, I went too fast. If you look at the fraction of the energy that actually gets trapped behind the horizon as a fraction of the impact parameter, you find that for the bigger impact parameters, which is where you have maximized your geometric cross-section, you actually are getting only a small fraction of energy trapped there. And if you actually ask what impact this has, if you do an impact parameter weighted cross-section, you find that it's an enormous effect. The dotted lines are the cross-sections without including inelasticity for x equals 1 to 6. And the solid lines are including inelasticity. And you find that your cross-sections go down by a significant fraction, especially for the higher dimensional case where it's a more important effect. And so you find that cross-sections are going down by factors of 100 to 1,000. It's really a big effect. And these are, again, for relatively low x min. So if you try to ask for x mins that you really trust, you're down to much lower cross-sections. So I think it's pretty safe to say that the black hole threshold is really much higher than was originally thought, both in terms of m black hole and in terms of the energy you would need to produce black holes with that particular mass. So it means, first of all, of course, you have lower production cross-section, a lower reach in black hole mass, and a lower reach in black hole entropy. So you're clearly not producing, or you're very unlikely to be producing, classical thermal black holes. So what is it that's getting produced? I mean, you still have these collisions happening, so is anything happening? So it's hard to know what's going on. This is obviously not a calcular regime, but you can ask questions like, what kind of multiplicities would I really expect if I collided together particles? So we just asked that question to see what's going on. So we cheated because we don't really think these are classical black holes, but we said, suppose you trust this and you actually use some sort of, you just calculated how many particles you would expect them to decay on average and asked what happens. And although it's unreliable, the conclusion we're going to find is obvious, which is that you're going to find low multiplicity final states in general. So what we have here are, for ADD and for RS, we have the rates to produce 6 particles in the final state. So we conservatively called a high multiplicity state 6 particles, which isn't at all clear that anyone would identify that as one of these explosions. But we said, suppose you just need 6 particles. And again, the dotted lines are without inelasticity, and the solid lines are with inelasticity. And so this is 6 particles, and then we asked how many times you get 2 particles. And you can see, just by eyeballing it, that 2 particles covers at least as much of the region as 6 particles, and if not more, and for RS it's the same. So then if you just make that explicit, you find that since you have at least as much regime covered by the 2-particle final state, which is the solid line, the wide solid line, as the 6-particle final state, which is the narrow solid line. Okay. So, first of all, it's not reliable to be a thermal state, and it has lower reach anyway. And so just what I'm saying is very intuitive. If you actually imagine going up in energy, the first thing you're going to see is some sort of strong interaction effect, where you're going to see the scattering effect in 2 particles, and then you're going to go to higher energies, and if you're very lucky, you would see some sort of multi-particle final state. But given that you don't really trust that they're black holes, we don't really trust that that's going to happen. So what Patrick and I decided to do was just face facts and say, probably what you might actually see some strongly interacting physics, some effect of quantum gravity, but it's probably not going to be in the form of black holes that we trust at all. So we just said, let's look at 2-particle final states, jets and leptons, and could we actually tell this apart from background? Is there anything interesting? And the answer is yes. I'll come back to the leptons later, but even for jets, the thing is, if you really have something coming from strongly interacting physics, be it gravity, be it anything, you expect more transverse events. You expect harder collisions and much more transverse events. QCD is dominated by T-channel exchange. It's much more forward, so there's large numbers of jets, but they're more forward. If you have something new, like a low quantum gravity scale, you should be able to see it. I mean, basically, it's residual from the fact that you expect black holes to be isotropic. For any strongly interacting physics, you would expect a much more transverse distribution. So what we suggest doing is that basically compositeness searches are sort of not really focused on these days. A lot of people don't believe it's technical or whatever. But I think compositeness searches have really been sort of neglected more than they should, because if there is going to be physics that is beyond the regime where we can just experimentally find the particles and study them and really discover them at some 5 sigma level, it's going to be very important to look at high energies and see, do we see extra effects of hard scattering that we wouldn't have anticipated. So what we suggest is just measuring these differential cross-sections and also measuring the angular dependence to see whether events look harder, more transverse. And in particular, there's a quantity that's been used in D0 already, and some CMS studies have considered it. They call it R eta, which is the number of events with the pseudo-rapidity parameter eta being between 0 and 0.5 divided by the amount between 0.5 and 1. So you're looking in the central enough region that we have some single detector, but you're asking for the really central ones versus the sort of not so central ones. And the reason they define this parameter is because a lot of the systematic errors in not knowing your energy scale would cancel. So even if you saw some cross-section that seems higher than background, you're not necessarily sure that you didn't get your energy scale right or something like that. So by having this parameter, you really can do something that's much less dependent on experimental errors. You can ask how we're going to know the difference between this and other strongly interaction physics, and that will become clear as I go along. But of course, we hope that we've actually found other evidence of extra dimensions that this particular idea is right. So I just want to clarify, because now I'm going to present some results for various models, and I really do mean models of quantum gravity. I'm not trying to derive it. I'm just trying to say that there could be a lot of information in the data that could actually tell us a lot of information about quantum gravity. And that's actually kind of nice, because it was just black holes that wouldn't actually tell us anything. I mean, very exciting, but it wouldn't actually tell us anything. But we're going to see that different behaviors might actually look quite different in this 2-to-2 scattering, and that might actually give us some information about what's really going on. And so I'm not saying that we can make precise predictions that I trust any particular model, but I want to show you how different different models could be in the type of behavior that you would find. So for example, let's just look at these dijet black holes. So here we just did the very simple thing. We just said, let's just take the black hole cross-section literally. We don't necessarily trust that these are true black holes with a horizon, but let's just take the cross-section as some estimate, this geometric factor, as some estimate of the number of events you get, and ask what you see as a function of energy. So the upper plot, again, it's ADD and RS. The upper plot is just the cross-section itself, and the lower plot is this quantity R eta that I've defined. So for the upper plot, okay, and so here we're just assuming a very rapid turn-on of the black hole cross-section. You would expect something probably much smoother than this, but it looks very different from just about any other model of strongly interaction physics you can have if there is some sort of evidence of a sort of strong threshold you might expect if this is in any way related to some quantum gravity physics. And this is just for various values of the mass, so the threshold would be at different quantities depending on what depending on what the quantum gravity scale is, m. What you see in the R eta is really beautiful. If it's just background, it's 0.6. These curves are just allowing for experimental error. But this is so this is 0.6 within this error. And if you have these black hole events, and again, we just took the cross-section quite literally, you find that you really be able to see, again, this very dramatic effect in this quantity R eta. And that's true, of course, in both ADD and RS. It really would be just an enormous effect. So although you might say, well, it's just 2 jets, who cares, that's really boring, you actually would see much more transverse distribution. So it really would show up extremely clearly if this is anything like reality. So as I said, there are distinctive features, which are the sudden turn on the cross-section, the transversality. And I just want to point out that even if we didn't assume that ridiculous turn-on at x min equals 1, even if you let it go all the way down to x min equals 0, there would be a lot of interesting information, because the threshold behavior, where the background is comparable to the signal, actually in the interference can actually distinguish different forms of the energy dependence of the cross-section. Basically, I think that if there is a low square, there's a reasonable likelihood to see some effects in 2 to 2. Now you might say, well, what a string theory is, right? String theory tells you that you turn off the transverse 2 to 2 cross-section. But actually, that's something really interesting to look for. So we just said, suppose that G string, we're in perturbative string theory, so we don't hit the black holes first. We first hit a perturbative string theory threshold. So we said, what would the resonance behavior look like? What would the 2 to 2 scattering cross-section look like? So we just, again, modeled this by putting in the Veneziano amplitude. And we actually took 2 different forms of the Veneziano amplitude. The original form and another form that seems to apply for supersymmetric theories. And you're going to see that it's really quite distinctive, the string behavior. And not only is it distinctive in and of itself, you can actually distinguish these 2 different forms of the amplitude, which is kind of amazing. And obviously, you can distinguish it from just a simple resonance like a Z prime. So let me just show you a couple of plots reflecting that. So here are what I call the stringy results. Again, this is a model of string theory. But let's see what we get with those Veneziano amplitudes. Well, you might get some resonances, which would show up in the cross-section. Of course, as things get wider, it's going to show up less and less in the cross-section and be harder and harder to see. But if you look at this quantity R eta, there's no way you would miss it if you have a relatively low string scale. Because what you see is it just really has this amazing behavior where it just drops off. And this is for various values of the string scale. And you might see a hint of resonance behavior, but you really would notice if you're looking in this transverse direction. I mean, it goes well below the standard model prediction, and in a way that's experimentally trustable. So if you have low-scale string theory, you would really see it in this 2 to 2 cross-section. And you can ask, if I see some resonance, I mean, how would I know if it's a string resonance or a Z prime? Well, of course, the answer is by looking, this is, I think I have these out of order. So this one is, how do I tell the difference from a Z prime? And so here we have our plot on the right. And you see that if it's a Z prime, you would just see the resonance and it would go away. Whereas if it's a string resonance, you would just see this really dramatic drop-off in the transverse cross-section for 2 to 2. And this plot is showing you that if you took a different form of the Veneziano amplitude, the one that had the 1 minus stuff in the denominator, you actually might get resonances, but this resonance doesn't actually, it turns out that in the original Veneziano amplitude, if you look at the first resonance, it actually gives you a completely isotropic distribution. So it doesn't modify the standard model distribution. So if you saw a resonance with no evidence of it in this quantity R eta, you'd actually be able to tell the difference between the 2 different forms of the Veneziano amplitude, which is quite amazing. And of course, if you saw these strings, you're probably not going to see black holes. This is probably all you would see, because the black hole threshold is so much higher. And as we saw, it was already getting too high. And the final model we looked at is just said, well, suppose you just had higher dimension operators. That's what we usually use for strongly interacting physics. And in quantum gravity, you can have lots of sources. It could be black holes, multi-graviton exchange, high-scale string theory. And again, an interesting aside is that you can actually distinguish the different forms of the Veneziano amplitude in terms of what type of operator they produce. The original Veneziano amplitude gives you a dimension 6 operator. The other form gives you dimension 8 only and higher. And string theory in warp space. And so you can ask a question about the energy dependence in this case. there's a few asides here which I don't have time to talk about now, but I can come back to. I mean, the nice thing about these higher dimension operators is that it's a way of incorporating a lot of information like gauge charge or spin structure, etc. And the result is, of course, that you should be able to see these higher dimension operators. That's the kind of thing people have already looked at. But you can see, just by eyeballing it, the behavior looks completely different than anything we talked about before for these models of quantum gravity. And just one final thing is that another really interesting thing that you find by looking at these different models is that another thing that can really distinguish among them is the relative fraction of leptons. If you really are making anything that's really gravity-like and has any type of black hole behavior, you expect a relatively high fraction of leptons, of order 10%. If you have some four-fermion operator, you would have a much smaller cross-section because you would have to have QQ bar structure functions rather than QQ or glue-glue, which could conceivably form these black holes. And if you have the QQ bar, then you're down a lot in the PDF. So you're down by factors of 1,000 or so. So by looking at the relative lepton fraction, you also have another real handle on what's going on. It's a way of telling you, studying questions like, does the charge spin off if you actually make these black holes, etc. So to summarize, I really don't think we're going to see high multiplicity black holes, and I certainly don't think we're going to see anything where we trust classical predictions. However, I think there's some really nice information that's been neglected for a while, which is that there could be some really interesting information buried in 2 to 2, even for Jeff's final states. And this initial increase in rate seems to always occur for any model you can think of if you have a low quantum gravity scale. And moreover, you can really make distinctions that one might not have thought is possible. I mean, if you really have some model for string theory, you really could tell them apart if you really are lucky. And admittedly, you have to be lucky and have this low scale. But it's interesting because whatever your favorite model of strongly interacting physics is, perhaps you have some funny anomalous dimensions. By looking at the energy dependence both of the cross-section and this quantity of R8, you're very likely to be able to tell different models apart. And it's a way of getting at scales that are higher than a few hundred GeV. You really can probe scales TeV to 5 TeV range at least. So you can really get to much higher energies, which I find quite optimistic, quite encouraging rather. And also, as I said, you can look for the threshold region where you can actually test the detailed energy dependence of whatever you have. There's a lot of interesting questions that still remain, asking about if you have some initial phase where you shed some of the charge and spin. I mean, you might see other interesting final states. Is that stuff soft and hard? I mean, there's just a lot of questions that haven't been asked yet, and I think could have interesting answers. So basically, our goal is to get as much information as possible. We want to think about models to make sure we're asking these questions as broadly as we can. We want to get at, I think it's really important to really ask how can we get to high energies. And I think compositeness studies or compositeness type studies might be a real key to some very interesting information. Thank you.
We're running a little late, but maybe we can have 1 or 2 questions. There's one.
Is there any hope of seeing quantum number violation?
Yeah, so that would of course be, I had that on one of the transparencies. That of course would be the most exciting thing, but basically because you're talking about TeV scale, if you have to have those be forbidden by some sort of gauge symmetry or some sort of separation in an extra dimension or whatever. Because if you had those, you would then be able to, suppose I saw mu E final state, which of course would be the most exciting thing, you could turn it around and get something like mu to E gamma if you have this happening at a TeV scale. So unfortunately, those most exciting things have to be forbidden somewhere in the theory. So then the question is, what could you see given that that's the case?
Okay, so let's thank Lisa again.